We are group number 21, and we're going to go over biocomplexity. What is biocomplexity? Biocomplexity is the study of complex structures and behaviors that arise in nonlinear interactions of active biological agents. This may range anywhere between molecules to organisms. Biocomplexity research institutions are working to address the challenges of human health, habitat, and well-being. They are using an information biological approach that utilizes technology to predict, explain, and visualize the behavior of massively interacting systems. In this presentation, we will be going over two research problems that are being studied, followed by a deeper look into how technology is being used to help biocomplexity research progress. Our first problem is going to be based on a research that is being taken in Biocomplexity Institute of Virginia Tech. Virginia Tech has a Biocomplexity Institute here where there are many research problems being addressed. One of them is focused on testing smart simulations to address unknown variables in immune response. The complexity of the immune system presents a serious challenge to researchers who want to mathematically model its behavior. No two people experience the same Crohn's disease. Genetics, environment, microbiome, nutrition, and medical history all play a role in how it is felt and how it should be safely managed. Advanced machine learning methods make it easier to consider all of those specific circumstances together, getting us a step closer to models that provide comprehensive and accurate predictions of each individual's response to illness and can inform the development of precision medicine interventions and predict the success of human clinical trials.
Our second problem is Rita Cowell's interview in the magazine The Scientist about using biocomplexity on cholera. The biocomplexity for him is just like how components of a global system interacting to the biological, physical, chemical, and human dimension, all taken together both to gain understanding of the complexity of the system and to be able to derive fundamental principle from it. Cowell's interview addressed his belief in being able to have a scientific understanding of sustainability, even perhaps a series of formula or questions developed by mathematicians to explain by define sustainability. He and his lab will be developed a predict capacity for the action taken with respect with the environment and predict the specific outcomes. They can't do this yet well, but they can predict, and it's not very precise and it's very quantitative. After investing the biocomplexity research, they were able to make prediction more and more specifically. And the collateral work has proceeded very hard, and they have been able to keep their lab at the University of Maryland. And just this month, they published the genome sequence of the Vibrio cholera, and his students in his laboratory before joining the Institute of Genomic Research, and people now accept that the Vibrio cholera is a bacterium naturally occurring in the environment, and it's associated with the zooplankton, and they have discovered it and using remote scenes, and the two peaks in the cholera epidemics in the Bangladesh are perceived by the poor cholera season increased the sea surface temperature in the Bay of Bengal.
Biocomplexity researchers use high-performance computers to run simulations and analyze data. The Biocomplexity Institute at Virginia Tech has 3 data centers made up of 500 servers, that total more than 4,000 cores at 22 terabytes of RAM. Their main hybrid cluster, Shadowfats, has more than 2,500 cores, providing 28 terabytes of RAM and over 1,200 terabytes of GPFS storage. Using their high-performance systems, researchers utilize various software tools to collect and analyze data and run simulations. One such tool is the Enteric Immunity Simulator Visual, which simulates immune responses in the gastrointestinal tract. In the example video, researchers modeled how inflammatory immune responses remove pathogens, how lesions are formed, and how regulatory immune responses restore the intestinal homeostasis in the gastrointestinal tract.
Now we have three main technical problems. The first one is cooling. For example, large data concepts generate massive amount of heat, which must be mitigated to keep the processor cool down at their optional peak. And without the water cooling, temperature can exceed 125 degrees, which could easily damage the computer core. To ensure the maximum functionality, large rocks outfitted with the Virginia Tech Biocomplexity Institute called multi-air jelly door rack cooling system allowed the institute to maximize the computing power within a small footprint. The second one is computing ability. Biosystem simulation requires a powerful computing power, which is difficult to generate computer. Even supercomputer can take a long time to simulate the calculation, and it's a good idea to apply dispute computing to biological systems. Even artificial intelligence to simulate biological complexity in the future is not a math. The third one is testing, but even though people can make the corresponding simulation calculation, the conclusions of the calculation are sometimes inaccurate, so we need to verify them. It also needs a supercomputer to do it, which will take a lot of time. And that'll be all. Thank you for watching.